Hello students, welcome back to the classroom point. In our today's class, we are going to discuss the Faraday calculations, equivalent mass calculations, as well as the Faraday's first law and Faraday's second law. So let's begin the class now. Faraday is represented by the letter capital F. So Faraday meaning is the charge carried by one mole of electrons is called Faraday. So let us see here. Charge of one electron is equals to minus 1.6022 into 10 power minus 19 coulombs. Here we said about the 1 mole. We know that 1 mole value, that is Avogadro's number, 6.023 into 10 power 23. So one electron charge is this much, and this many number of electrons charges is equals to, now let us multiply it, charge of 1 mole of electrons is equals to, so let us multiply both of these, and here this negative sign we don't take. This negative sign represents the attraction between the nucleus and the electron. That's why this negative sign do not have any importance in solving the questions. So that this we shall remove, only number we take here. So here it is equals to 1.6022 into 10 power minus 19 coulombs into 6.023 into 10 power 23. This value is equals to 96,487 coulombs. Approximately accepted value is 96,500 coulombs. So this 96,500 coulombs is the charge of 1 mole of electrons. Charge of 1 mole of electrons is called as the 1 Faraday. So that's why here I can write down that 96,500 coulombs is equals to 1 Faraday. So 1 Faraday is the charge of how many moles of electrons? 1 mole of electrons. So that I can write down the 1 mole of electrons. So wherever this 1 mole of electrons is used, there I can use the 1 Faraday word instead of that 1 mole of electrons. So let us take some calculations here. Example questions. Let us take sodium ion. 1 mole of the sodium ion is added with the 1 mole of electrons. So 1 mole of the sodium needs 1 mole of electrons to deposit as a sodium metal. This 1 mole of sodium ion's mass is 23 grams. This is equals to 1 mole, which needs 1 mole of electrons. This 1 mole of electrons charge is called as the 1F, that means 1 Faraday. So wherever 1 electron is there, that means 1 mole of electrons are there, I can use the 1 Faraday. It deposits 23 grams of the sodium. That means entire sodium gets deposited by using the 1 mole of electrons or 1 Faraday of electricity. Now let us take the other example, that is magnesium 2 plus ion. This magnesium 2 plus ion atomic mass is 23 grams per 1 mole. When you add 1 Faraday of electricity, 1 Faraday of electricity meaning is 1 mole of electrons. So that here out of 2 positive charges, only 1 positive charge gets neutralized, the other positive charge do not get neutralized. So that here we can write down that Mg plus. See here Mg2 plus is carrying the 24 grams of the mass. That means this 24 grams of the mass belongs to the 2 charges. It has to be distributed between the 2 charges. Each charge is getting, each positive charge is getting the 12 grams of the mass. Then by sending the 1 Faraday of electricity, only 1 charge gets deposited, other charge do not get deposited. That means out of 24 grams, only 12 grams of the mass gets deposited, remaining mass not gets deposited. So that you can write down that 12 grams of the magnesium gets deposited. by sending 1 more Faraday of electricity, or else again 1 mole of electrons, the other positive charge, remaining positive charge also gets deposited. Now that is 12 more grams gets deposited. At a time, if we send 2 Faradays of electricity, then this 2 Faradays of electricity meaning is 2 moles of electrons. So that it completely neutralizes the entire Mg2 plus N that has the 24 grams mass. So that entire magnesium gets deposited 24 grams. Now let us take the aluminum Al3 plus, whose mass is 27 grams per mole. Now 3 positive charges are there. So by sending first Faraday of electricity, Al2 plus, that means out of 3 positive charges, only 1 positive charge gets deposited. So this 27 grams has to be distributed among the 3 charges now. Each charge will get the 9 grams. That means now out of 27 grams, only 9 grams of the aluminum gets deposited. By sending 1 more Faraday, 1 more 9 grams gets deposited. By sending 1 more Faraday, the remaining 9 grams gets deposited. If you send 3 Faradays of electricity at a time, then all the aluminum gets deposited. That means 27 grams of the aluminum gets deposited. Now, writing these equations is not acceptable in this manner, but I am explaining this concept only to make you understand how the charges are going to deposit. Actually, aluminum will take all the charges. For example, let us take here magnesium. I have taken the 1 mole. By sending the 1 Faraday of electricity, 1 mole meaning is 6.023 in 10 power 23. So 6.023 into 10 power 23 number of magnesium 2 plus ions mass is 24 grams. By sending 1 Faraday of electricity, so 1 Faraday of electricity cannot deposit all the positive charges belongs to the 24 grams. It can do only the half of the mole. That means 3.01 into 10 power 23 20th number of Mg2 plus ions charge only gets deposited. That means half magnesium gets deposited plus remaining half Mg2 plus do not gets deposited. So half mole gets deposited. Complete mole mass is equals to 24 grams. Half mole of the magnesium mass is equals to 12 grams. This is the way to write down the equation. By sending the 1 more Faraday, remaining half mole of the magnesium gets deposited, so that giving the 12 more grams. So only to make you understand about the deposition process by using the Faradays, I am taking the charges like this in a sequential manner. So that's here also you have to take out of these charges, number of moles gets deposited is equals to number of moles deposited is equals to number of Faradays we are sending divided by charge on ion. That means here by sending the 1 Faraday of electricity, how many moles of aluminum gets deposited is 1 Faraday I am sending, so that number of moles of aluminum deposited in this case is equals to 1 Faraday divided by charge on the ion, that is equals to 3. Remaining 2/3 is not getting deposited. So only 1/3 mole of the aluminum gets deposited. So this is the calculation using the moles wise. But for understanding purpose, I am using this sequence. So here aluminum by sending 1 Faraday, only 1 charge gets deposited, that's mass is equals to 9 grams. By sending 1 more Faraday, remain 9 grams. Again by sending the 1 more Faraday, the last 9 grams gets deposited. Altogether, if you send the 3 Faradays of electricity, so 27 grams of the aluminum gets completely deposited. Now, let us take the case of the copper, Cu2 plus N. Cu2 plus N atomic mass is 63.5 grams. By sending the 1 Faraday of electricity, Cu plus deposited, it is deposited as Cu plus, that means 31.75 grams of Cu copper deposits. By sending the remaining Faraday, remaining 31.75 grams of the copper gets deposited. By sending the 2 Faradays of electricity, at a time entire copper gets deposited, that is 63.5 grams of the copper gets deposited. Now let us take one more example, that is zinc, Zn2+. Zinc atomic mass is 65 grams. By sending 1 Faraday of electricity, Zn+, that is 32.5 grams of mass gets deposited. By sending 1 more Faraday, remaining 32.5 grams of the mass of the zinc gets deposited. So why? Because this 65 grams has to be distributed between the two charges. So every charge gets 32.5 grams. So by sending the 2 Faradays of electricity at a time, the entire zinc gets deposited, that is 65 grams. Now let us take the silver, Ag+. Ag plus 1 mole mass is equals to 108 grams. By sending the 1 Faraday of electricity, so that entire silver gets deposited as 108 grams. This is in case of the metals. Then in case of the non-metals, then how to calculate it? For example, if you take the H plus M, by sending the 1 Faraday of electricity, since it is a non-metal, it will not get deposited, but it is released, it is evolved in the form of the hydrogen gas, so that a half mole of the hydrogen gas gets evolved. So half mole of the gas at STP occupies 11.2 liters. Or else in terms of the mass, you can write down 1.008 grams of the hydrogen is released. Now let us take next one, oxygen, CO2 minus. Now in reaction, instead of taking the electrons, it is releasing the electrons now. So that it is releasing the electrons, half O2 gas is released and 2 Faradays of electricity is released. So 1 Faraday of electricity, 2 Faradays of electricity carries half mole of the oxygen. That means 2 Faradays are able to release the half of the oxygen. Half mole of the oxygen, that means volume is equals to 11.2 liters. 1 mole of any gas at STP occupies, 1 mole of any gas at STP occupies 22.4 liters of the volume. In bars it is 22.7 liters. So 2 Faradays involving, that means half mole means 11.2 liters. But for 1 Faraday, if you calculate, this value is equals to 5.6 liters of the gas is being released. Now one interesting thing is that in all these calculations, let us connect this equivalent mass with the number of Faradays here. So how to calculate the equivalent mass of the sodium here? Equivalent mass of the sodium equals to atomic mass of sodium divided by charge of the sodium, that is equals to 23 grams is the equivalent mass of the sodium in this case. And in this case, equivalent mass of magnesium is equals to atomic mass divided by valency of the ion, that is charge, that equals to 12 grams. And equivalent mass of the aluminum is equals to atomic mass 27 grams divided by charge is equals to 3, that means 9 grams. Equivalent mass of the copper in this case is equals to atomic mass 63.5 grams divided by charge of the copper equals to, that is 31.75 grams. Now equivalent mass of the zinc, 65 the atomic mass, charge is 2, that is equals to 32.5 grams. And equivalent mass of the silver, atomic mass is 108 grams, charge is 1, is equals to 108 grams. So in these cases, by sending 1 Faraday of electricity, whatever the mass is deposited is equals to their equivalent masses. See here, 1 equivalent mass, that means 1 Faraday deposits 12 grams. 12 grams is the equivalent mass here. Here 1 Faraday of electricity deposits every time 9 grams only. 9 grams is the equivalent mass. Here 1 Faraday of electricity for copper deposits 31.75 grams, which is the equivalent mass of the copper. For zinc also same thing. 1 Faraday deposits 32.5 grams, which is the equivalent mass of the zinc. For silver, 108 grams deposited by 1 Faraday, which is the equivalent mass of the silver. That means 1 Faraday of electricity always deposits 1 equivalent mass of the substance. So what is the 1 equivalent mass? It is very simple, that the mass that belongs to the 1 unit charge is called as equivalent mass. It may be positive charge, it may be negative charge. See here, I am taking the example of magnesium only. Magnesium is having the 24 grams of the mass for the 1 mole, Mg2 plus M. But if this mass is distributed between the 2 charges, then every charge will get the 12 grams. The mass of every charge is called as equivalent mass. In this case, every charge is getting 12 grams. That's why the equivalent mass of the magnesium is equals to 12 grams. So when you send the 1 Faraday of electricity, that 1 Faraday of electricity deposits only that particular charge. Means that particular charge mass gets deposited. So that mass is nothing but the equivalent mass. So from this it is very clear that 1 Faraday of electricity always deposits 1 gram equivalent mass of the substance. Then in case of the gases, see here, 1 Faraday of electricity liberates 11.2 liters of the hydrogen. Then how to deal with the in terms of the gases? Let us see here. Calculation of the equivalent volume. Equivalent volume is equals to equivalent weight divided by molecular weight into 22.4 liters. Equivalent volume of the hydrogen is equals to equivalent mass of the hydrogen is 1.008 grams divided by molecular mass is 2.016 grams into 22.4 liters. So it cancels as 11.2 liters. Similarly, equivalent volume of oxygen is equals to equivalent weight of the oxygen is 8 grams, molecular mass is 32 grams, and volume is equals to STP of 22.4 liters. It goes 4 times and it gives the 5.6 liters. So in terms of the gases, 1 Faraday of electricity always liberates the volume of the gas that is equals to their equivalent volume. So for mass of the substances, 1 Faraday deposits 1 gram equivalent mass of the substance, but for gases it always liberates the or evolves the 1 equivalent volume of the gas. So we shall write down that one here. One Faraday of electricity always deposits 1 gram equivalent. You should not misunderstand that what is 1 gram equivalent. It is not the 1 gram actually, 1 part mass in grams. Here 2 parts are there. Every part mass we are taking in the grams only. Here 1 gram equivalent means 12 grams. Means 1 part mass is 12 grams. So this 1 meaning is number of parts, mass in grams. So that 1 gram equivalent of substance or liberates or evolves 1 gram equivalent volume of a gas. So 1 Faraday always deposits 1 gram equivalent mass of the substance or liberate the 1 gram equivalent volume of the gas. That is in case of the hydrogen 11.2 liters, in case of the oxygen it is equals to 5.6 liters. So from this it is clear that if you understand here, see from here to here number of Faradays increases. So when number of Faradays increase, mass of the substance deposited also increases. See if we send the 2 Faradays of electricity at a time, then 9 plus 9, 18 grams gets deposited. By sending the 3 Faradays of electricity, 27 grams gets deposited. That means when the number of Faradays increases, number of equal parts deposited also increases. So that here we can get the one more relation, that number of Faradays is equals to number of gram equivalents. This is one of the important formula in solving the questions for both Faraday's first law as well as the second law. And we also know that number of gram equivalents formula, number of gram equivalents is equals to weight by equivalent weight. Now substitute this value here so that we will get the weight by equivalent weight. So that we can write down that weight by equivalent weight is equals to number of Faradays. Now send the equivalent mass the other side so that mass of the substance weight is equals to number of Faradays into equivalent mass. So let us see here in this case. For example, let us take the example of this magnesium only. Mass of the magnesium deposited by sending 1 Faraday of electricity. By sending 1 Faraday of electricity, 12 grams of magnesium get deposited. So that let us see how to calculate number of Faradays. I am sending the only 1 Faraday, 1 into equivalent mass of the magnesium. Equivalent mass of the magnesium is 12 grams. So that 12, that gives 12 grams. So this is for 1 Faraday. Mass of the magnesium gets deposited by using the 2 Faradays of electricity. How much? 24 grams. Then how to get this 24 grams means number of Faradays into their equivalent mass gives the mass of the substance deposited. In this case it is for 2 Faradays of electricity. Then already we have done that number of moles deposited. Number of moles deposited is equals to number of Faradays divided by charge on the ion. See, in this case, if you send the 1 Faraday of electricity, already we have calculated number of Faradays is 1 divided by charge on the ion equals to 3. At a time, if for example, if you send the 2 Faradays of electricity, then 2 by 3. If you send the 3 Faradays of electricity, 3 by 3 is equals to 1. That means complete mass of the 1 mole of the aluminum gets deposited. For gases, see here we have calculated the weight for the metals that gets deposited. In terms of the gases, the number of Faradays equals to number of gram equivalent volumes in terms of the gases. Number of gram equivalent volumes. Then how to calculate number of gram equivalent volume? Number of gram equivalent volume is equals to volume of gas at STP divided by equivalent volume of gas at STP. So by substituting this value here, we get the relation between the volume of gas divided by equivalent volume of gas is equals to number of Faradays. Now if you want the volume of the gas liberated is equals to number of Faradays into equivalent volume of gas. That means, example, by sending 2 Faradays of electricity, so how much volume of the hydrogen gas is liberated at STP? So volume of hydrogen gas liberated at STP is equals to number of Faradays is equals to 2 and equivalent volume of the hydrogen gas is equals to 11.2 liters. So that directly we can get the 22.4 liters of the gas. And in case of the oxygen, volume of oxygen liberated by 2 Faradays of electricity. So 2 into its equivalent volume is equals to 5.6 liters, that is equals to 11.2 liters. So already we have calculated how to calculate these equivalent volumes. So equivalent volume calculation already done. Using that we can use the calculation of the volume of the gas liberated by sending the some number of Faradays of the electricity. Now let us calculate pH calculations using the number of Faradays. Calculation of pH. First let us see the formula of the pH. pH equals to minus log base 10 concentration of the H plus ion. Here square bracket represents the concentration. So this concentration always to be taken in the normality. So let us relate the normality now. Normality is equals to number of gram equivalents divided by volume of solution in liters. Number of gram equivalents is equals to number of Faradays. So in the place of number of gram equivalents, I can substitute the number of Faradays, so that normality is equals to number of Faradays divided by volume of solution in liters. So this normality is nothing but the concentration. So in the place of the concentration of the H plus ions, I can use the number of Faradays of the electricity passed through the solution along with the volume of the solution. So that pH is equals to minus log base 10 into number of Faradays divided by volume of solution in liters. So by using this formula, we can directly calculate the pH of the solution after sending the some amount of the electricity through the solution. So now let us begin the Faraday's first law. First law of Faraday. So Faraday's first law says that the mass of the substance deposited or volume of the gas evolved at any particular electrode in electrolysis is directly proportional to the quantity of electricity passed through the solution. Passed through the electrolyte solution, or this may be melt. Solution may be in the liquid form also, not only in the aqueous form, even liquid form also. So this entire definition clearly says that if you send the more amount of the current, mass of the substance deposit directly proportional to the quantity of electricity we are passing. If you send the more quantity of electricity, more mass of the substance gets deposited. Already we have seen weight of substance is equals to number of Faradays into equivalent mass. So that when the number of Faradays increases, equivalent mass of a particular substance in a particular compound remains constant. So when the number of Faradays increase, weight of the substance deposited also increases. So here the Faraday's first law also says the same thing, directly proportional to the quantity of electricity in coulombs passed through the electrolytic solution or in the electrolyte liquid. Now let us derive this same formula using this equation terminology. So this clearly says that mass of the substance deposited is directly proportional to the quantity of electricity in coulombs. So that I can write down that weight of the substance is directly proportional to the quantity of electricity passed through the solution in coulombs. So here Q is equals to coulomb. 1 coulomb of electricity, or else number of coulombs. You can take the number of coulombs. We know that 1 coulomb is equals to I into T. 1 ampere of current passed through the solution for 1 second of the time. So coulomb is equals to current in amperes and time in seconds. You can substitute the value here also. So the W is directly proportional to the I into T. Now let us replace this proportionality symbol. So now I am going to introduce W equals to some proportionality symbol Z into I into T, where Z is equals to, it is known as electrochemical equivalent. And this value, instead of the I into T, we can write down W equals to Z and Q also. Now let us define what is the electrochemical equivalent. Here Z can be written as Z equals to W by Q. Q meaning is quantity of electricity in coulombs. If we send only 1 coulomb of electricity through the solution, that time whatever the mass of the substance is deposited, that is equals to electrochemical equivalent. If you take 1 Q, then Z equals to W. See here, there is a little confusion among the students, that you should remember that when you send the 96,500 coulombs of electricity, that is what called the 1 Faraday. The mass of the substance deposited is known as the equivalent mass of the substance. But by sending the only 1 coulomb of electricity also, some mass of the substance gets deposited. That mass of the substance is known as the electrochemical equivalent, that is Z. For these many coulombs, mass is called as equivalent mass. For only 1 coulomb, the mass of the substance is called as the electrochemical equivalent. Now here, what are the units of the Z? See, it is equals to weight by Q. Weight means here we are taking the grams, and Q is equals to coulombs. So when you are sending the 1 coulomb of electricity, or else 1 ampere of the current through the electrolytic solution for 1 second of the time, that time whatever the mass of the substance deposited is known as the electrochemical equivalent, that is equals to Z. Now let us try to relate the electrochemical equivalent with the equivalent mass. So from this it is clear that 96,500 coulombs of electricity deposits some mass of the substance, that is called as the equivalent mass. See, 1 coulomb of electricity deposits the mass of the substance Z. Then 96,500 coulombs deposits how much mass of the substance, that is called the equivalent mass. So equivalent mass is equals to, now do the cross multiplication, 96,500 into Z by 1 coulomb. Z into 96,500 divided by 1. So equivalent mass is equals to electrochemical equivalent into 96,500, that is called as the 1 Faraday. Okay. Now let us try to substitute this Z value. What is Z value here? W by Q is there. So that here equivalent mass is equals to mass of the substance divided by Q into 96,500 coulombs. Q can also be written as I into T. So that I am going to write down E is equals to W into 96,500 divided by I into T. But I would like to calculate the weight of the substance deposited in a particular reaction. So that W is equals to equivalent mass into I into T divided by 96,500. This equivalent, this is one formula now. Equivalent mass of any substance is equals to atomic mass divided by valency, or valence is also known as n factor, into I into T by 96,500 coulombs. Atomic mass by valence is known as the C equivalent mass, and I into T by 96,500 is a new term now for us. Number of Faradays is equals to Q by, that means Q 96,500, current in coulombs by 96,500, or else I into T by 96,500 coulombs. So in the place of I into T by 96,500, I can write down the number of Faradays. So finally we are reaching the formula that W is equals to atomic mass by valency means equivalent mass into I into T by 96,500 means number of Faradays. This is what formula earlier we discussed. So entire relation is connected to the again equivalent mass and the number of Faradays that we already discussed in our previous classes. Now let us see here. We will get some other information from this formula. Send the atomic mass this side. So we get the weight by atomic weight for atoms, for molecules weight by molecular mass is equals to this I into T by 96,500 I am writing as a number of Faradays divided by valency means charge of the ion. Charge on ion, since n factor for redox reactions it is the change in the oxidation state. So that here weight by atomic weight is known as the number of moles. Number of moles of the substance deposited is equals to number of Faradays divided by charge on ion. Already regarding this calculation, we have done one calculation using the magnesium and aluminum also. So example I will take once again. Aluminum 3 plus by sending the 1 Faraday of electricity Al, 2 plus it will be by sending 2 Faradays of electricity Al, plus it will be by sending the 3 Faradays of electricity it will be Al. That means number of Faradays 1, 2, 3. So first case number of moles of aluminum deposited, number of Faradays by charge, that means 1/3. Second case number of moles of aluminum deposited, number of Faradays by charge, so that 2/3. Third case number of moles of aluminum deposited, number of Faradays by charge, 3/3 is equals to 1 mole of the aluminum gets deposited. Now usually in the electrolysis process, whenever these some substances are deposited, some substances are deposited at cathode and some gas are liberated at the anode. In those cases, then comparison comes the number of moles of the substance deposited or released at anode and cathode. Then how to connect this one? So let us connect this one using this particular formula. Number of moles of substance is equals to number of Faradays divided by n factor or charge. When number of Faradays is same, when number of Faradays is same, that means when you are sending the same quantity of electricity, then the relation between the number of moles of the substances that is either deposited or evolved at different electrodes of the same electrolysis process is equal to C. We can write down that number of moles is inversely proportional to the n factor, that means charge of the ion. So here I can write down that number of moles of the gas released at anode or cathode is equals divided by number of moles at cathode is equals to n factor of that particular substance present at the cathode divided by n factor of that particular substance present at the anode. So by taking this relation, we can get the ratio of the number of moles of the substances either liberated or deposited at a particular electrode in the electrolysis process. So now let us see the Faraday's second law. Second law of Faraday. So in the first law of the Faraday, only one electrolytic cell is taken. So in the case of the second law of the Faraday, we take the series of electrolytic cells. Let us see here. Three different electrolytic cells I am taking. And electrodes are placed like this. So in first electrolytic cell, I am taking the copper sulfate solution. Second electrolytic cell, I am taking the silver nitrate solution. Third electrolytic cell, I am taking the aqueous sulfuric acid. Now this Faraday's second law says that when same quantity of electricity is passed through the various electrolytic cells connected in a series, then the mass of the substances deposited or the volume of the gas liberated at the respective electrodes is directly proportional to their equivalent mass. I'll write down the definition and we'll back to the explanation again. When same quantity of electricity is passed through the various electrolytic cells having various electrolytes and connected in a series, then the mass of substance deposited or volume of gas liberated at various electrodes is directly proportional to their respective equivalent weight for metals and equivalent volume for the gases. So now if you see that copper is present in the Cu2 plus form here, silver is present in the Ag plus form, and H2SO4 H plus ion plus SO4 2 minus ion. When you send 1 Faraday of electricity through all these electrolytic solutions, then 1 Faraday of electricity deposits only one equivalent part of the copper, that is 31.75 grams of the copper. But 1 Faraday of electricity deposits 108 grams of the silver, and 1 Faraday of electricity liberates 11.2 liters of the hydrogen gas. That means 1.008 grams of the hydrogen. So 1 Faraday of electricity is not depositing same mass of the substance. It is depositing only one equivalent mass of the substance. That means if the equivalent mass of the metal or the element is more, then more mass of the substance gets deposited. That means it is clear that even for the equal volume, equal current you are sending through the electrolytic solutions, same mass will not get deposited. It depends on their equivalent masses. So that here weight of the copper deposited is directly proportional to its equivalent mass. Weight of the silver is directly proportional to equivalent mass of the silver, and volume of the hydrogen is directly proportional to the equivalent volume of the hydrogen. But remember that by sending the 1 Faraday of electricity, only one equal part gets deposited everywhere. Here also one positive charge, one positive charge, one positive charges. That means only one equal part. Here also one equal part, one equal part, one equal part. Means number of equal parts are equals to same. That is called as the number of gram equivalents. So number of gram equivalents of the substance deposited is same, but mass of the substance deposited is not same even for the same quantity of the electricity passing through the various electrolytic solutions. So that here we can write down that number of gram equivalents of copper is equals to number of gram equivalents of silver, that is equals to number of gram equivalent volumes of hydrogen. Then how to calculate number of gram equivalents? Weight by equivalent weight. So that weight of copper divided by equivalent weight of the copper is equals to weight of silver by equivalent weight of the silver, that is equals to volume of hydrogen by equivalent volume of the hydrogen. So by knowing this, if two solutions are connected in a series, by knowing the equivalent mass and mass of the substance deposited, we can easily calculate the mass of the substance deposited in the other electrode. So dear students, I hope you understand today's class. So we completed the Faraday's calculations, Faraday's first law and second law. Using your respective textbooks or the materials, please try to solve the questions. All the explanation is done in today's class using the various formulas also. Use these formulas, you will get the answers very easily. Thank you one and all. So we shall meet in the next class.